Welcome to Topic 4 in Mate 210 Materials Engineering on defects and strength. Let's take a look at the big picture to see where we've been and where we're going with this topic. First of all, remember that the big picture involves four key components. The composition, or what a material is made out of, and the processing, how we affect the physical shape of the material, together determine the structure of the material. And that structure then determines the performance of the material, or its properties. In Topic 3, we focused on the structure primarily, looking in great detail at the crystal structure of metals, ceramics, and polymers. In Topic 4, we'll begin to look at what are called crystalline defects, or naturally occurring mistakes in the crystal structures of these materials. And it's a consequence of these defects that we have specific mechanical properties, particularly plastic deformation. So we'll focus on the plastic behavior of these materials, especially metals, in Topic 4 as well. Let's look at an application, and I want to start with an application of turbine blades. Turbine blades are found in what's called the turbine section of a typical jet engine. This is the turbine section back here, where the hot gases from combustion are passed by a series of blades which then extract that energy to drive the shaft, which then turns the compressor stages up in front of the engine. Now, in turbine blade technology, there's two key things going on. First of all, the blades are spinning, which means they're under very high stresses as a result of centripetal forces. Secondly, they're exposed to high temperature exhaust gases, which have detrimental effects on their performance. Well, here's what some blades look like. These are turbine blades over here, a variety of different sizes of blades. You can see they come in very small sizes. Those would be the very first high pressure turbine blades, all the way back to very large, what are called low pressure turbine section blades. You notice they have these little what are called Christmas tree attachments on the bases of the turbine blades, and that Christmas tree slides into the rotor, and you can see this is the rotor over here. These are the more blades stacked up on the rotor, all inserted, and you can see from their cross section they look like airfoils, which is exactly what they are, as their job is to extract energy from the airflow passing by them. Well, I mentioned that there were two key things going on with turbine blades, one being the high loads. Turbine blades are spinning at something in the neighborhood of 14,000 RPM. That's extremely fast. And that high rate of rotation causes large amounts of centripetal forces. And those forces apply tremendous stress, particularly at what's called the blade root, which is where the blade itself matches the base where the Christmas tree attachment is. So you can see in this FEA model that the high stresses here are causing a lot of inelastic strain or plastic deformation. So this is a map of plastic deformation that's occurring inside the turbine blade. So what you don't want is to see large amounts of plastic deformation in the turbine blade, because that would obviously change the dimensions of the blade and therefore change its behavior. In addition to the plastic deformation, we're also facing high temperatures. So the same FEA model, now looking at temperatures, plots the temperatures at the blade tip to be close to 930 degrees Celsius. That's very hot. It's close to 2,000 degrees Fahrenheit. So you can imagine that putting these materials under extreme temperature and large amounts of plastic strain can cause a lot of damage to the turbine blades. So what we want to understand is it possible to manipulate the material so that you don't have to worry about that plastic deformation and the effects of the high temperature? And the answer is yes, we do that in modern turbine blade technology. Now here's what can happen when the turbine blade itself fails. And so what we see here is a phenomenon called tip rub, where the blade has stretched under plastic deformation at high temperatures to be too long, and the blade actually rubs up against the outer casing of the engine, causing damage to the tips of the blades, which then ruins the effect of the blades as an airfoil. And you can see this is an example of extreme tip rub damage on a turbine blade. Now, one solution to this problem is to use what we call single crystal turbine blades. And if I remember, I'll bring in some examples of crystal and turbine blades into class to show you. But on the left, we have a picture of what's called a polycrystalline turbine blade. And if you look very closely, you can see small blotches on the surface of the blade, right where the cursor is pointing. Those blotches are individual grains. Remember, we talked about grains and grain boundaries in Topic 3. Those are individual grains inside the turbine blade that you can see on the surface. Now, if you had the microscope and could look at this single crystalline blade over here on the right, you'd notice there are no blotches. In fact, this entire blade is made up of one single crystal, all stacked with exactly the same orientation. In other words, there are no grain boundaries, and therefore no physical appearance of grains that you can make out. And the reason for this is that by having a single crystal, we can manipulate and control the orientation of that crystal so that we get the maximum performance.